Let's continue with our lecture on mathematical methods. We were looking at the complex analysis. Today we are touching on an important topic about singularities and residue theorem. It's a very important theorem from the application point of view because most of the application of complex analysis comes because of this theorem. It's very useful in evaluating real as well as complex integrals. So let's have a look at it. So we are looking at the singularities and residues. This is a part of a course PH3103 at IISER Kolkata. Before going into singularities and all, let's have a look at the Taylor's theorem. So this is an important theorem, but you might have come across this in the real analysis too. So let f of z be an analytic function within a domain D with the z0 be the point inside domain D. Then f of z has a series representation given by f of z as a k going from 0 to infinity, fk of z0 divided by k factorial z minus z0 to the power k. So here this represents the kth derivative, and then you look at this equation. It is very similar to what you come across in the real analysis. The power starts from k is equal to 0. That means you essentially have a polynomial, but it does not terminate. We are starting from k is equal to 0 and going all the way to infinity, various powers of z to the power k. So clearly this function is analytic and we don't have any problem. So this is the main implication of the Fourier series, that analytic function can be represented in the powers of z. This expansion is valid for the largest circle C with the center z0 and the radius r, such that it entirely within the domain D. So the proof, I am not going on the proof very carefully. I just state that it can be done by simply rearranging the Cauchy's theorem or playing around with the various terms. You will find that we often use this step, what is called then a miracle occurs. Though you might want to go very seriously over it, or we may want to explicitly work it out. You can work it out and you can take any complex analysis book, you would find the proof. But you must have come across this in the real analysis, and this is why playing around with the Cauchy's theorem you can get the proof. But I am not really going over this. This lecture is slightly going to be painful in that respect, that I am stating two of this theorem without really proving them. But emphasis is that you need to know these results to have a better understanding, while the proof really it does not matter. So you can sit and prove it by yourself if you want to, but we are orienting more towards the application, which we will do in this lecture. Singularities of a function f of z. If a complex function f of z fails to be analytic at a point z is equal to z0, then the point z0 is said to be singularity or a singular point of the function. So idea is very simple. If the function is not analytic at a point z0, then the point z0 is said to be singularity of the function. Example, taking a trivial example to make it quick, f of z is equal to 1 by z is singular at z is equal to 0. Singularity plays an important role. We have more definitions coming now. Let us see what is the meaning of isolated singularity. Suppose f of z is equal to z0 is a singularity of a complex function f of z. The point z is equal to z0 is said to be isolated singularity of the function f of z if there exists some deleted neighborhood or a punctured open disk with the radius capital R, such that z minus z0 is between 0 and R for given z0, throughout which f of z is analytic. Okay, so it is good to have some idea of how this is done with the help of diagram. So we have a region or a domain D in which we have defined a function f of z. This function f of z has a singularity at z is equal to z0. Now we call this as an isolated singularity if we could take a neighborhood or a disk around z0 and remove those points. Let the radius be r. It can be any arbitrary radius as long as there is a single simple region which we can remove out, and then we look around the function in the remaining domain. If it is analytic, then the singularity is called the isolated singularity. So that means we should be able to remove a neighborhood from the singularity and rest of the function should be analytic. So that is a understanding of isolated singularity. So let's look at the example. We have a function f of z is equal to gz by z minus z0 to the power n, where g of z is an analytic function in the entire complex plane, or it is called the entire function. For n greater than 0, we have z is equal to z0 is an isolated singularity. So this is a trivial example. I am just emphasizing that what kind of a form comes in the isolated singularity, that is to explain. I have given this example. Let's look at the more practical example. Let's take a function f of z is equal to z by z square plus 1. In this case, gz is z, and we have a denominator z square plus 1. We can clearly see that at z0 is equal to I and z0 is equal to minus I, we have singularities. That means we can look at this complex domain. We have plus I and z1 is equal to minus I. At this point, this function is not analytic, so we call them singularity. We can dig out a small region, open circle around these points, and then remove this, and the rest of the plane is all right. That is f of z, z by z square plus 1 is analytic outside these two open disks, and then that is what we actually need to show that this is an isolated singularity. Isolated singularities are common and comes very frequently in our analysis. Now we get to another important theorem, which is called the Laurent's theorem. Let me first state that let f of z be an analytic within an annular domain D defined by r less than z minus z0 modulus less than capital R. Then f of z has a series representation. F of z is equal to some k going from minus infinity to plus infinity, ak z minus z0 to the power k. So this is valid in an annular region, that radius capital R and a small r, and it lies in the region between them. Now important difference here, f of z is analytic in the annular region only between the two disks, and we are not saying anything what happens to outside this, and there could be singularities there, and especially if the z0 is a point which is singular, then we can have a Laurent's expansion about that point. And the coefficient ak can be given as ak is equal to 1 by 2 pi I contour integral over contour f of s minus z0 to the power k plus 1 ds, k going from 0 plus or minus 1 plus or minus 2 and so on. Because where the contour C is a simple closed curve lies entirely within the domain D and Z0 in its interior. So it is much easier to explain with the help of a figure. So we have a domain in which we have defined the complex function f of z, but it is analytic only in an annular region around a point Z0. That means we have two circular regions, capital R and small r, and we have a function which is analytic in this green shaded zone, and we are not interested outside this region. And another important point to notice is that it is less than. We are also not worried about the value of the function, whether it is analytic or not, on this circle or the contour itself. We are interested only in the interior of these two annular region, and then the point Z0 lies within the inner radius of R. Circular regions are centered around Z0. Now our function is analytic in the green annular region, where it can be expressed in terms of Laurent series, where the coefficient AKs are given as a contour integral, where the contour described should be containing the point Z0. It can be arbitrary simple contour, but it necessarily should contain the point Z0. For example, we cannot have a contour of this shape because it does not contain the Z0. Point Z0 itself is not inside this domain, the region which we are interested. That means Z0 need not be analytic. That is why we have a power of Z minus Z0 minus K. So that means that the function need not be analytic. It can be having poles of different order. If the function is completely analytic, then we can have a Taylor series. If the function is not analytic at a point, then we can cut out a small region and we can form an annular region in which we can express the function as a Laurent series. Again, I am not going through the proof of this. Again, one can work it out, but proof is again a digression. What we need to understand is how we apply this and useful to define various properties of the singularities. Based on the Laurent series, because Laurent series definitely tells possibilities having a singular point at z is equal to z0. So this leads to the classification of a singular point based on the Laurent series. An isolated singular point z is equal to z0 of a complex function f of z can be classified based on how it is expanded in the Laurent series as follows. First one, we call it the removable singularity. In the Laurent series, we have both z to the power minus n and plus to the power minus n. The coefficient corresponding to the negative powers are called minus ak, or principal parts, and if all of them are 0, then we have left with the Laurent series only with the positive powers of z, and such a point, singular points, are called removable singularity. You might ask, why bring in the singularity at all? You can simply define the Taylor series. But you could have a singularity because the way the function is defined. And one of the classic example which one immediately understand is f of z is equal to sin z by z, or the sinc function. We see that it looks as if it has a singularity at z is equal to 0, but when we expand this in terms of series, then we see that there is no singularity at z is equal to 0, or the limit z going to 0 in this case is a finite, and that is because of all the negative powers of Laurent series, 0 coefficient, and we have only positive term, and that is why we say it removable singularity. The next type singularities are called the poles. Poles comes in the Laurent series as if all the coefficient a minus k are 0 for some n greater than 0, for some finite n, then such singularities are called the poles of order n. A quick example is 1 by z minus z0 to the power n. Here n is a given number. Beyond for all k greater than n, we have a coefficient a minus k is 0, and our series terminates at the value of minus k is equal to n. Such singularities are called poles with the order n. Now the simplest one which we have is when n is equal to 1, function of the type which is 1 by z minus z0, and that we call as a simple pole. In a Laurent series, if all the coefficient corresponding to negative powers are 0 other than power 1, that is only a minus 1 remain, rest of are all 0, such isolated singularities are called the simple poles. So you have a form of a function of this type. You can make it a simple table here showing what should be the form of the function for the in terms of Laurent series. If a point z is equal to z0 is a removable singularity, then we can represent the function like this. We don't have a z minus z0 to the power minus k. All the powers are from 0 to positive n only. If it has a pole of order n, then we have a minus n is non-zero, and all the a minus k's greater than n is 0, and then the function takes the following form. You have power series terminate for the negative n, and then you have a pole of order n. The simple pole is in which we have all the coefficients are 0, and only we have a term of 1 by z minus z0 and the positive terms. Then we have a simple pole. Then what we have is called the essential singularity, where all the powers till minus infinity to plus infinity are there, and then nothing can be done about this singularity, and these singularities will be always there on your complex plane. Okay, let's look at the definition of residue. This plays an important role in the rest of the complex analysis. The coefficient a minus 1 of z minus z0 in the Laurent series is called the residue of the function f of z at an isolated singularity z0, and it is denoted by coefficient a minus 1 is equal to residue f of z at z0. Residue can be easily calculated if you have a Laurent series. Let's look at the some of the methods how to calculate the residues. For a function f of z is equal to z0 has a simple pole, then the residue can be calculated. A minus 1, that is residue of f of z at z0, can be calculated by taking the limit z going to z0, z minus z0 into f of z. So this would give the residue for the simple pole. If you have a pole of order n, then you can calculate with the following procedure. Let f of z has a pole order n at z is equal to z0, then the residue a minus 1, residue f of z at z0 is given by 1 by n minus 1 factorial limit z going to z0 dn minus 1 dz n minus 1 into z minus z0 to the power n f of z. It's basically finding the coefficients of minus 1. So we got to make all the coefficients below 0 by taking the limit, and then rest of the things what remain is the residue. So for if the simple pole is there, then you can multiply z minus z0, then the coefficient a minus 1 becomes a constant, and the rest of them get multiplied by z minus z0. As a result, limit z going to z0, rest of the term going to 0. Why the coefficient of a minus 1 is so important? You might ask, why need to work so hard to get them? The answer is very simple. We have what is called Cauchy's residue theorem. Again, this is a Cauchy's theorem. If you are unwilling to say Cauchy again and again, and you can simply call it a residue theorem. Let D be a simply connected domain, and C is a simple closed contour lying entirely within the domain. If a function f of z is analytic on and within the contour C, except at the finite number of isolated singularity z1, z2, etc. at zn within C, then we have integral over contour C f of z dz is equal to 2 pi I sum k going 1 to infinity residue of f of z is equal to zk. That means the integral of the function over a contour with the finite isolated singularities can be simply given by the 2 pi times sum of all the residue. So this is a very important theorem, helps to calculate the contour integration. Let's have a look at the picture. We have a domain D in which we have defined a function f of z, and we have a smooth contour, and then we have a few singularities. In fact, finite isolated singularity z1, z2 and zn and so on. We can of course construct a finite open disk and remove it. Rest of the region, the function is going to be analytic. Then we can say that the integral of f of z dz over the contour C is going to be simply 2 pi times the sum of all these residue at z1, z2 and zn. By looking at this figure, it is clear how to prove this theorem. All you need to do is use the Cauchy's theorem again, then rearrange some of these terms to get the integral as a sum of residues. Suppose C1, C2, Cn are the circles around Z1, Z2 and Zn. This is possible because this is an isolated singularity. Suppose further that each circular Ck has a radius Rk small enough so that C1, C2, Cn contours are all mutually disjoint and inside closed contour C. So this is can be done because these are isolated singularities, and we know this can be done, and from Cauchy's theorem, integral over contour C f of z dz can be written as a integral over this contour. It is a sum of integral over all these contour, that is k is equal to 1 to n integral over closed contour ck f of z dz, and that is simply reduces to be sum of the residue at f of z zk multiplied by 2 pi I. So this is a rather interesting theorem, and you can see the proof is also very trivial following the Cauchy's integral theorems. Let's have a quick example to see how it is useful in evaluating the integral. Let's evaluate the integral f of z is equal to 1 by z minus 1 square into z minus 3 square. So this is a function which we want to integrate, and the contour is given as a rectangle described by x is equal to 0, x is equal to 4, y is equal to minus 1 and y is equal to plus 1. So let's first look at the singularities. We have two singularities. At z is equal to 1, we have a second order pole, and at z is equal to 3, we have a simple pole. In this case, it is trivial to figure out the singularity because it's already written in the required form, and then we can draw it on the complex plane and see what happens. We have a singularity at z is equal to 1, and we have a singularity at z is equal to 3. Then we have a rectangle which is described by this, and we can see that both these isolated singularities are within this contour. So we got to consider both these. Now our first step is to calculate the residue of the function at z is equal to z0. We know that if the function has a pole of order n at z is equal to z0, then the residue is given with this cumbersome equation. And then if the singularity is a simple pole at z0, then it is a fairly straightforward. You simply multiply it by z minus z0 and take the limit value z going to 0 to compute the residue. Let's compute the residue at both these singularities. At z is equal to, for f of z has a pole of order 2 at z is equal to 1, and the residue f of z at z is equal to 1 is given by limit z going to z0 d by dz 1 by z minus 3. So you can substitute in this equation, and one can compute this in a straightforward manner, and residue turns out to be minus 1 by 4. And then, and the other case, for z is equal to 3, we have a simple pole and it is straightforward. You simply multiply it by z minus z0 and take the limit z going to 3. Here we get the residue is equal to plus 4. Using the residue theorem, we have an integral of 1 by z minus z1 square into z minus 3 dz is given as a 2 pi into residue at 1 and residue at 3. Since these both residue comes with the negative sign, their sum is 0. Value of this integral is 0. We have seen that if the function is completely analytical, the integral is 0. But in this case, even if we have two singularities, one is a pole of the order 2 and another is a simple pole, even then their effect seems to be cancelled with each other, and we have a integral of the function on the contour given is going to be 0. This is an interesting way of evaluating integral, so we will do more example in the coming videos. Let me stop here.